Okay, we are going to start our discussion of chapter 5 on this thing called recurrence relations. To start with, let's do some trigger activities. The first one is the Tower of Hanoi. Not sure if you have ever played this game before. It's a very simple game. It goes like this though. What you see here is actually this thing that you see here, the stick, okay, is called a peg. And of course, then there are the discs. Okay, there are the discs. So the game rule is there that you're actually intending to move these discs from one of them to either this one or this one, doesn't matter which one, either one of them. And as you move them from one peg to the other one, you must move in such a way that at all times the smaller one must be on top of the bigger disc. At no instance can you have a bigger disc on top of the smaller one in any of the pegs. Right, this is the rule of the game. So if I may use this notation again, say this notation again. So there are three pegs, right? Let's call them peg A, B, and C. So supposedly in the instance where there's only one peg, one disc, okay? I call this one, and of course, okay. I number the disc one as the disc with the smallest radius. Okay. So if later on if there are two discs, I'll number them as 1, 2. 1 being the small one, 2 being the bigger one. Okay. So if there's only one disc, our job here is to find the number of ways that we can do so. To move that one disc to the next peg. How many ways, or how many steps do we need? Sorry, steps. Where steps? Sorry. How many steps? Thank you. How many steps? Okay, how many steps? Right. So for this one, you start on this one, and then I do this on the next iteration, and then therefore the number of steps in there is okay. So when in the event that n is 2, in the end that n is 2, which means I start off with 2 discs. I number them 1 and 2. So when I number this way, right, the one on the left, the 1 is always on top of the 1, 2. You know, 1, 2, right? 1, the disc is on top of the disc number 2. So the question is, how do we move so that how many steps do we need to move this into the next peg? So one way to go about it is 1 being on top, right? I leave the 2 behind. I move the 1 over first. Hey, hi, come. Okay, right. This is only one step, right? One step. Then what I do next is I now move these 2 into the C. Right. Then lastly, I move the 1 into the C. So in that way, right, I'm able to move the disc 1 and 2 from A, this case, to C. And I did it in 1, 2, 3 steps. So answer is 3. Okay. So now I like to do it for the next case. A, B, and C. Now I got 3 discs. I number them as 1, 2, and 3. Okay, let's hear from the first person. Suggest how should I move?
You only have 1.
Right. I gotta leave the 2 and 3 behind. I move the 1.
The next one is also only 1.
Okay. Then the next thing is
No, you can't put a larger one on top of it.
Yeah, but you can put the 1 back on it.
Yes, you're right.
I think this is incorrect. I think you want to move the 1 to C.
It doesn't matter.
It doesn't matter.
I wouldn't.
Yeah, it doesn't matter.
okay. So now we want to move the 2 away, right? Into C. and then remove 1, 2. Very good.
Your 3 to be.
Very good.
Your 1 back to A. Yeah, and then you put them all together.
No, cannot be so fast.
Move your 2 to B.
No.
And then move your 1 back to B.
Yeah. Lah. No, just you gotta move the 2 first, right? You can move 2 first. So altogether, how many steps do you take? 1, 2, 3, 4, 5, 6, 7. 7 steps. So now if you have n this, the question mark is what is this number? So what you have worked out just now was when n is 1, when n is 1, right? 1, 3, 7. So what we have is you are set up a table like this. Number of this, and then number of steps. 1 this, and then just now we have calculated, right? We have done 3 and 7. When it's 2 is 3 steps. When it's 3 this is 7 steps. Oops. So now if you have n this, what is this in terms of n? Okay. So if I were to use the notation, this means T1. Okay. This means T2. This means T3. That means this means Tn. So it's like a number pattern that you're trying to establish, right? How do we work out the value of Tn? Some people will do it by recognizing the number pattern. Has anyone done the case when n is 4?
Yeah, it should be 15.
Do you say 15?
Yes.
You tried it's 15.
I powered.
Yeah, I powered it.
CS students.
Right, it's 15.
Oh, I lose. You lose.
I think it's 15. Okay, so when it's 4, the people here say it's 15, and I think you are right. So the question is, how do you do it for the case when you have n this? Okay. So one way of trying to solve this problem is to first and foremost establish a recurrent relation between Tn and Tn minus 1. So give yourself, don't say up, no, don't spoil. So let's see if you can recognize a relationship between Tn and Tn minus 1. And if you are able to establish a relationship, that relationship is called a recurrence relation. So give yourself the 30 seconds, and then let's see if anyone can suggest. And to suggest this, right, you might want to think, what is going to be T5?
Actually, without this in terms of number of states, then you actually have it being much clearer.
Is it? Wait, never mind. So maybe if I ask Pranaya, what do you think is T5 going to be?
T5 is going to be 31.
Okay, so he says 31, and I think he's right. Pranaya says T5 is 31, so you recognize a pattern. So what's the pattern that you recognize, Pranaya? That
2 to the n minus. Okay, Tn equals to Tn minus 1 plus 2 to the n minus 1. No, wait, there's no 2. Okay, actually, you can also do that. Yeah, you can also do that.
Okay, so this is what Pranaya has gathered now, that the next iteration is always the earlier one times 2, then plus 1. If you look at this game, can you give a qualitative explanation why it ought to be like this? Why should it be like that? Why should the next iteration be twice the first? Sorry, be twice the earlier one and then plus 1. So looking at this game, right? Now looking at this game, could you give a reason why it should turn out be like this? Say for example, if I'm talking about doing T9, right? Why should T9 be twice T8? Can you give a qualitative explanation? This is 9, right? This is 9. This is what? 1, 2. Wait, it's not 9, is it 9? 1, 2, 3, 4, 5, 6, 7, 8 only. Is it 9? 1, 2, 3, 4, 5, 6. I see 7 only. But doesn't matter. Let's say for example T9. Okay? T9. Why should T9 be twice T8 plus 1? Is there anyone who can offer a qualitative explanation? Yes, let's hear from Marcus R.
Because T minus 1, remove everything except 1. You here, then you move 1, then you move everything on top.
Good explanation. So he's trying to say, to do 9, right? You have to move the 8 on top to one side first. That gives you T8 ready. After moving the 8, right, you need the one step to move the biggest disk over to the next pad. And then you repeat the thing to move the first 8 to join hand the biggest disk level. Very good. Okay. So that being the case, based on this we can actually generate our pattern. T1 is 1, right? T2 is equals to 2 times 1 plus 1. How about T3? T3 is 2 square 1 plus, okay, lame again, very lame of writing it this way. Agree not? Twice of the earlier plus 1. T4 is okay, let me just write this way again.
Yeah, it might be a better idea. Yeah.
Alright, at this counting, you therefore come to the conclusion that Tn is equals to why are you touching this one, right? Okay. And then from here what do?
You just say that 2 to the n minus
You can use the GP formula. Right. Pranaya trying to tell me this, right? You're trying to tell me this one, is it? Yeah. So Pranaya has therefore, okay, so to speak, he has therefore solved the recurrence relation. This afternoon, gentlemen, right? Pranaya has actually provided a solution to the recurrence relation. What is the recurrence relation? It is Tn equals to twice Tn minus 1 plus 1.
What is recurrence?
Good morning, Mr. Lim.
It's afternoon meeting. Yeah, I gotta redo it again.
You're gonna come here and say good evening.
Good afternoon, Mr. Lim.
Good afternoon. Okay. So what's happening here is we are talking about recurrence relation. We'll come up with the first example. In the first example, right, this is a recurrence relation that Marcus Ahn was able to explain the why. Okay, this recurrence relation for latecomers, right, came from this game, the Tower of Hanoi. So Marcus Ahn was able to explain how this recurrence relation relates to the game. And then we had Pinea, who actually so-called solved the recurrence relation. Okay. So in this first trigger activity, we have a very good explanation from Marcus Ahn, followed by the solution given by Pinea. Now, so what happened is in the solution, like what you do in your computer science studies, when you encounter questions that have iterations, you will try to write down a pattern, and from there you try to solve it in like what we have done here. Alternatively, there's another way to go about it. If you believe that if this is the given recurrence relation, after many attempts, you believe that the solution to such a recurrence relation will always be like this. For this recurrence relation, if you believe that it has to look something like this. It means you second guess that, hey, based on your experiences dealing with this kind of recurrent relation, you believe that the solution looks like the red color. You can try, and what do you try, What you can do is, if you have this belief, then you say, hey, let's try, okay, let's try. Based on what we know from here, that my T1 is 1 and T2 is 3, I'm going to do this now. I'm going to say T1 equals to 1 implies that A times 2 to the power of 1, which is just 2, plus B is equals to 1. And because T2 is 3, right? This becomes A into 4 plus B is equals to 3. So if you believe that this is the kind of a solution, right? If you believe that the solution would look like this, you can then solve this equation simultaneously to obtain that A is actually and B is equals to, and you get the same solution, therefore Tn is equals to and between the two approaches, one approach that you saw just now is what you do if you do it in your computer science lessons. You try to do the number pattern, or in the lower years when you deal with number pattern, you deal with number patterns, right? You do something like this. You will try to write down the number pattern, and from there you try to deduce a way to solve, which is clever, which is what you would do before I told you about this second way. And in this chapter, believe me, okay, in this chapter we are trying to advocate to you the second way. Okay, why the second way? Because second way is quite fast to cook, good to eat. I finally say it's very easy. If you recognize that every kind of a recurrence relation of that nature in the yellow box, you recognize that their solution will look like what is in the red color here. Okay, let me highlight it in like green. If you believe, which can be justified when you try to do the iteration, you can do a few times. Realize that every time a recurrence relation is in the yellow color, the solution will be in the green color, and that provides you with a shortcut as compared to the complete iteration that we did and applying GP formula or AP formula or whatever formula you know to get to the summation.
If we change it to be something like dn equals 3n minus 1 plus 1,
Then it'll be A,
still be in
there'll be A 3 power n plus b. Yeah. Yes, Kenneth.
But how do you deduce that it's just 2 plus 2 to the power 2, like from 3 to 7? Like I still.
3 to 7, is it?
Yeah.
Okay, you missed it. You missed it. Okay, the number pattern that we generated according to Pranaya was twice the earlier, then plus 1.
Oh.
3 times 2 plus 1 is 7. 7 times 2 plus 1. And then if you're going to wonder why this recurrence relation actually answer the question of this Tower of Hanoi, you got to buy Marcus Arm a drink. And then he'll tell you. You missed it. Marcus was explaining to the class.
Which Marcus?
Marcus Ang. Okay, not to worry, we have another trigger activity to entice you. Alright, so I want you to have a mindset ready to know that actually in this chapter, we are trying to offer you an alternative way based on observations made, based on known results, that such recurrence relation, the yellow patch, will always have a solution, the green patch. And if you hold to this belief, then it's quite easy to solve. You know, nothing stops you from going back to the iteration and but it doesn't take a long time. And that way is what you have been doing all your life. Right? In your CS, when you try to do the search, binary search or whatever search through the tree, you probably iterate this.
How do you prove that this is true? Yeah. For like not true, for like 3 or 4 or 10? How do you prove it?
Okay, so now I'm getting a question from Vikram. No, Vikram says, how can we be so sure that the solution will always look like this? You know what I mean? Okay, that's why I'm here to sell you this this message. No, believe. Wow. Okay, so this will left something for Vikram in the next lesson to explain to you, to ask why you have to believe that way. I can't offer you one offhand, to be honest, but it is with this observation that each time you solve the question, it always turns out like this, and it's with this observation that we, just like last time we do DE, right? Do DE. I'm not sure if you still remember the second order. When they have constant coefficient.
Yeah, but that one you can't show. That one you don't need to do.
Okay. So Vikram, could you one day show us a justification? Yeah.
Okay, there's some number sequences that breaks the pattern, right?
Break this pattern. I mean, you're trying to say there are some recurrence relation that look like a yellow, but it do not turn out like a green. Are you trying to say that?
Yeah.
Okay. So Kenneth, you will enlighten us the next lesson. Give us an example. Okay. I'd like to see it because I do not know. To be honest, I do not know. Okay. So Vikram, if you could kindly do some research and then convince us. Okay. Yeah. So this note doesn't provide a true justification. It's just to sell you the belief. Okay, so this is one trigger activity, and I hope you are sure by it. That one is the pizza problem,
Pizza?
You know what? When boys gather together and share food, and there are so many boys, they want pizza. If you have 2 persons to share, it's very easy, just cut straight. If you have 3 people to share, or 4 people to share, you cut into more slices. But as all people, we always want to maximize the piece of pizza. We want to cut it into so many pieces that I can give up to as many people as one. But in this question, we are not worried about the sizes that you cut into. We just want to know with the straight cuts, how many pieces can we get? Like for example, right, when I do 1 cut, I get 2 pieces. When I do 2 cuts, in this case, I get 4 pieces. Admit that the 4 pieces are not of the same sizes. With 3 cuts, I get that many pieces. The question is, Okay. Each time you cut, you want to get the maximum number of pieces, right? So the question is, in n cuts, what is the maximum number I can have? Okay, let me put it in perspective again. Number of cuts. Maximum pieces. Okay, one cut produces, two cuts produces 4. 3 cuts, I can see from here, right, it's 1, 2, 3, 4, 5, 6, 7. 有没有？ How many pieces do you think you get? Oh yeah, I'll tell the number again. I'll tell the number again. You get 11. Okay, I'll tell you. Let's see, you can see the pattern. Say in the case of 5, Ryan, what do you have? 16, right?
God, us 6.
Yes.
Okay, I'll ask,
7.
11.
So same thing. So the question then is, if I call this one T1, T2, T3, T4, T5, and therefore there's Tn, right? Okay, there are 2 ways about it. One way is, you're very clever, you see T1 as 1 plus 1. Yep. Okay, Ryan, how do you get T4 and T5, Ryan?
You can't use
breakdown. Yeah, breakdown right here. This pattern, right? Yeah, this pattern.
Each part needs to go through all of the previous parts, so you are creating n more pieces.
Magic.
Okay, so thanks for this. Hang on, let me just show Marcus this way first, so you can see things.
But will it always be possible to cut all the previous stuff?
Yes, in math land. Yes, it will always be possible, yes. Because lines must intersect the world.
And the truth is, to do the 4th cut is not easy. That's why it's not shown here. Yeah. Okay. Let's see who can do the 4th cut. Who can do the 4th cut? The 4th cut is not trivial. Okay. Let's try again. Let me try again. Let me try on the board again. Thank you. 1 cut. 2 cuts. You just make sure that when you cut right, you cut through the earlier 2 lines. 3 cuts. 3 cuts right now. And then the 4th cut, you must make sure you go through the first 3 lines. You must go through the first 3 lines. Do I have a pen? I don't have one. Okay, let me show you. You must make sure that you go through the first 3 lines.
Whoa. And how you go through it?
And then the 5th cut become harder, see? Yeah. That's why when you cut, maybe when you want to do it on 5th cut, you mustn't draw your thing, you may draw it a bit tilted so that you can do a 5th cut. So you can cut it in such a way that the next cut can cut the other 4 or other 5.
How can you show that it's possible?
Okay, so Marcus is talking about the feasibility of actually doing it. Right. Marcus will tell us the next lesson. Yeah, so Daniel and Marcus are going along the same direction. The 2 of them will discuss and tell us whether or not we can do it perpetually. Because the question that Marcus and Daniel is thinking is, no way because come to a point, it's very hard to achieve that kind of thinking that I was trying to advocate,
Yeah, it comes about the
okay.
I mean, the pattern, there really isn't a pattern. It seems like you have a pattern, but it's not.
and then the next card is like that. You should cut the earlier 4, something. Then now it get harder, it's true. I appreciate what you say, what you was thinking. Yeah, so is it possible? At least theoretically, theoretically it's possible. But in actual fact, I don't think it's easy. So for this question, if you are very smart, you got very good eyesight, you observe this, which is what you will always do, as a kind of a math number pattern question. You do this, you recognize this through your sharp instinct, good eyesight, and experiences. You saw that it is like that. Email. Okay, the Hanoi Tower, is it? Okay, so based on this, right? Based on this, right? If I ask you what therefore is Tn, you will quickly tell me that it is this. Right? You tell me immediately that it is like this. Right? So this is your Tn. Because you know all your AP, GP and so forth. So if you solve it this way, it is the good old way. The good old way of doing things. However, we can also look at this same problem by establishing firstly a recurrence relation. What is the recurrence relation? We can see here that the Tn is always equals to the earlier one plus so now the question mark is, can we do this same question the way we did earlier? That means the belief. And Kenneth found his answer. When the number in front is not really anything other than 1, right? It's okay, no? But when it's 1, like in this case, right, the coefficient of Tn minus 1, right, is 1, you can't really do it that way, It's not going to work. Okay? You can't do the belief way, the belief. But because if it's 1, right, then you can go back to do it using the, okay, let me write down this again. If our recurrence relation is like that, we don't need the belief, we have a better way. What is a better way? We can actually create a summation of this and say that this is equals to, tell me if you find this statement that I'm writing down too hard for you. We have done this in year 1, is it? Or year 2? And on the left hand side, I'm going to do something called, okay, let's see if you can recall the name of this thingy. Not Ministry of Defense, no. Method of differences, right? Method of differences. Maybe have I? Okay, maybe I have an issue, T0. I'm going to stuck. Okay, I'm stuck. I am stuck because the way I have written, I have a T0. Okay, we got take T0 as 1, is okay now. Our question is about cutting right now. With no cuts, right now, with no cuts. Right, very good. So using method of differences, the left hand side becomes Tn minus so-called T0, and right hand side is the usual. and then therefore you get this. Wrong. Okay. So you realize that belief method that I did in the earlier question, the green patch, it won't work, you know. You try to do it in the case where the coefficient of Tn minus 1 it won't work. You know, it won't work. It's not going to work. Okay? So with these trigger activities, I hope that you will spend. Yeah. This one is it? Yeah. Okay. You just have list out the terms. You just have list out the terms from this summation. And you see a lot of cancellation. I was doing all the listing in my mind. Yeah. So I hope that with this, you are triggered, you know, that you will go home and finish the whole of chapter 5 because you are so fascinated by what we have just discussed.
I am so fascinated on what we just discussed.
Really?